So welcome. In this lecture we're going to talk about data structures. So in the course so far we've seen data types, and data types have been ways of modeling something we want to represent in a computer program. We began with early examples such as modeling a hand of cards, modeling an individual card and its components, a suit and a rank, and we built that up into a model of a whole hand of cards using a list-like data structure. We've also seen some other examples. So other examples of data types that we've looked at was the expression data type that we used to represent arithmetic expressions so that we could manipulate them, evaluate them, modify them, and so on. Today we're going to look at data structures. So data structures are not just about modeling something, but really it focuses more on the way that we model things. In particular, the way that we store data. And the way that we choose to store data in general is very much dependent on what we want to do with it. And so data structures is the study of ways of storing data for a particular purpose that make it efficient, effective, fast to perform the operations on that data that are interesting. Now, it's useful to understand data structures in a slightly different context, and that's the context that we're going to look at today, something called an abstract data type. So you can think of an abstract data type as being like a data type, but where we don't talk about how we represent the data concretely, but the kind of things that we want to do with the data. So it's typically described in terms of the operations that we want to perform on the data. And this is independent of the way that the data structure is used, which data structure we choose to implement the data type. So it separates the specification, or the interface, the way we interact with the data, from the way the data is represented. So then, in those terms, a data structure is a particular implementation of an abstract data type. And what's interesting about this way of seeing things is that it separates the use of the data type from the implementation. And in particular, in the construction of software, it means that if a program is using a data type, it doesn't have to care too much about the way it's represented internally. And in fact, we can start off with a very simple representation, which maybe is not very fast or efficient. And we can improve it over time without having to change the program which uses that data type. Hopefully these things will become much clearer once we get into some examples. So what we're going to look at then today is two examples of abstract data types. Queues and lookup tables. And queues are corresponding to the intuitive concept of a queue. We're going to see a couple of different ways of implementing a queue. And we're going to also look at an efficient way of implementing a lookup table. We've seen one way of doing that using lists. And this is not a terribly efficient way of representing a lookup table. And we'll look at a classical way of representing that in a more efficient way that allows us to look up things more quickly. So let's start to the first example, and that's the concept of a queue. So what is a queue? Well, it's some concept that is used widely in real life, but also in computer programs. We may want to represent data of various forms that arrives and leaves. And the main structure of a queue is that there is a notion of a front of the queue. So that's where things leave from the front of your queue. And when you join a queue, you join at the back. So it's an ordered sequence of things where the main operations on that sequence of things is joining a queue and leaving a queue. And then we use these kind of structures in computer programs very often. For example, if you are sending files to a shared printer, there is a queue that ensures that they're printed in the order that they arrive. Or there may be lots of different jobs to perform in some computation, and you want to perform them so that the first come, first served, that is the oldest job, is run before any newer jobs. And all of these things require a representation of the data that implements this concept of a queue. Now, you know from real life that there are notions of queues that we deal with every day, and the implementations of those can be very different, but the end result is the same. The people that arrive first get served first, even if it can be an inefficient implementation and involves you standing in a line, or a more efficient one involving taking a number ticket and being served in the order that the tickets are taken. So just like in real life there are different ways of implementing the same basic idea, we also see this in software and in computer programs. So what we're going to look at then is the first example today is an implementation of a queue. And we're going to look at two versions, one which is in some sense rather inefficient, and another one which is more efficient but won't be involved taking numbers. In fact, it'll be quite a different representation. So let's switch to a editor buffer here and start looking at what we expect from a queue. So the first version of a queue we're going to look at, and you can tell that one of the main features of it, we're calling it a slow queue, but the main thing is that a queue, an abstract data type like a queue, has an interface. And that interface consists of a bunch of functions for creating and manipulating queues. So we're going to introduce shortly, we haven't done it yet, a new data type to represent a queue. This will be the implementation, this will be the data structure that we're going to use. But independently of which choice we make, the thing that we want to implement are a bunch of basic operations on queues. For example, a test, a function for creating an empty queue. A function for adding an element to a queue of elements to get a new queue. That'll be the slightly bigger queue. So that'll be the result of conceptually adding the element to the back of this queue. And the reverse operation that we get called remove, which is the queue we get by removing the first element. So this is, we start with a queue and we remove the first element, we get back a queue. Now this actually would be an operation that can fail. It will fail if the queue is empty. So in that context, then it's rather useful that we also have a predicate is empty to actually test whether a queue is empty. And similarly to the remove, which removes the first element from the queue, we also have a function that gives us the first element. So if we were to put this element back on the queue that we got by removing, we should get back to where we started. And that's a little hint that we'll be actually interested in defining properties to specify properties of any implementation of such an interface we expect to be true, regardless of how we implement it. So what is a good way of implementing a queue data type, a queue of things, and it doesn't matter what's in the queue? Well, we have a data structure that's pretty handy for that kind of thing, and that is a list. So we could represent a queue of things using a list. And representing a queue using a list will be the most straightforward, but not necessarily the most efficient. So let me just derive a couple of functions here in case we need them at some point. I don't think I'll need eq, but certainly show will be very useful. Okay, so having chosen to represent the internal representation of a queue using a list, we can now get on with the job of defining the basic operations that we want for queues. So the empty queue is defined by the constructor for building a queue, and the contents of the queue, which will be represented by the empty list. Adding an element to a queue, we have an element A and some queue. Let's construct a queue and the remaining elements. So what we need to do is put the new element at the end of the queue. And what is the end of the queue? Well, we're representing a queue by a list. So we have to decide whether the front of the list is the front of the queue or the front of the list is representing the back of the queue. So I'm going to represent the front of the queue using the front of the list. So the new element that joins the queue has to not go at the front, but at the back. So to put an element at the back, we use an operation that we saw when we were defining the reverse function naively, the simple version of the reverse function. To put an element at the back of the list, we need to use the append operation in that way. We make a singleton list, a list of just one element, and we join it with that. And in this way, we put the new element all the way at the far end of the queue, at the end of the list that represents that queue. Okay, that was the add function. What about the remove function? Well, we're going to do pattern matching in a similar way, but remove will only work if the queue is non-empty. So we're going to pattern match on the non-empty list in that way. And we're going to then generate the queue that we get by removing that first element, namely the rest. And we can make that a bit clearer if we use the don't care pattern, but that's not so crucial, so I won't bother about that now. What about the front of the queue? Well, the front of the queue, that's a very similar operation. We take the queue of the same shape and return the first element. So this is the queue that we get after removing the first element, and this is the first element. Now, when is a queue empty? When is a queue like that empty? Well, again, we could use pattern matching for this, but I'm going to use a little bit of pattern matching, but I'm going to fall back on the standard list operation null, which tests whether a list is null. So a queue is empty if the list inside it is null. It is the empty list. Let me just tidy those guys up, and we have our first implementation of the abstract data type of queue. And this is going to serve as our reference implementation for when we implement a smarter version and not such a slow queue. So this is called the queue. This is wrapped up in a module called the queue slow version of the queue, and we're going to use this to define the fast version, or rather to test the fast version. So at this point you may be wondering why I've been referring to this queue as a slow queue, or queue slow as I wrote in the code. And the reason for that is that the way that we've represented a queue using a list is such that removing an element from the queue using this operation is very easy, because we just take the first element. That means it's relatively quick. We just look at the list, and if it's non-empty, we return the rest of the list, and getting the front of the queue similarly. It takes one step. But where we pay the big price is when we add something to the list. And that's because lists are cheap to access things at the beginning, but expensive when you want to access things at the end. And that's because we have to use this recursive function append, or however it's defined. It's going to be defined ultimately in a way that means the number of steps it takes to put something at the very end of a list is roughly the same as the length of the list that you're adding to. So if we have a big queue, the cost of adding one element, the number of computation steps that it takes, will be proportional to the length of that list. So if you have a million elements in your queue, then just adding one more element requires you to kind of step by step get all the way to the very end of this list in order to place the new element at the end of the queue. And that's an expensive process. So what we need is a way to do this more cheaply, because choosing your data structure representation here is the key to having efficient code. So here's the idea. Instead of representing a queue as a list with a sequence of elements where removing something is very fast, but adding something is very slow because we have to start at the front and work all our way down using the append function to finally get to the end before we can join the new element. What we're going to do is try and get the best of both worlds, a representation which is both fast to remove and fast to add. So what we do is we're going to represent the list into two halves, and actually how big these two halves are is not the main point, but let's suppose we split this one down the middle. The two halves will be representing the front of the list and the back of the list. And what we're going to do is use a list to represent each of these. So we're using two lists instead of one. But the trick is to represent the back half of the list in the reverse order. So this one list will be represented by two lists in this shape. And what that means is, just like before, it's going to be quick to remove elements, but it will also be quick to add new elements, because the new elements get added to the front of the back half of the list, and removing removes them from the front of the front half of the list. So both operations will be cheap. Now, it's not absolutely free, because every once in a while we'll have to take all the elements here and shuffle them around, in other words reverse them, and put them into the front of the list. So as soon as this list gets empty, we have to take these guys, reverse them, and put them back into the front. So you can think of this as like two waiting rooms. One waiting room for people arriving and one waiting room for people leaving. And whenever the waiting room for people leaving is empty, all of the people in the arrivals waiting room shuffle into the leaving waiting room. So that will incur a bit of a cost, but it's a cost that will sort of even out over time. The number of computation steps that we perform will be just one extra step for each element that we add to the queue. So the overall, the average, the long-term average cost will be much more efficient than the old representation. So that's the intuitive idea. So let's go back to the code and see how we can implement that. So I'm creating a new module. So this is I'm calling it a queue this time. I'm going to do some testing. So I've imported quick check. And I've also imported my slow queue, my queue slow, and I'm going to call it slow in this context, and I'll show you what that means. So what I have now is the same template I had before. I want to implement exactly the same interface. The implementation is undefined, and I'm going to use a couple of lists, but I'll show you that in a moment. Okay, so let me just save this Let's see if we can run this. Okay, so we've compiled the skeleton version of this code where everything is undefined except the data type, which I'll talk about in a moment. But the main thing I wanted to show you at this point is that we have access to the slow implementation of a queue. And we have that access by slow dot and then the name of any of these functions, like empty for creating the empty queue, or slow dot add 1 to the slow dot empty queue, and we create. So we have access to the old queues. You notice that they are, the show function doesn't use this name slow, it still uses queue, but we don't get mixed up between the two kinds because we have two different constructors. And in particular, we have the slow queue constructor, which is the thing which, when you give it a list, gives us the slow representation of a queue of things. So this is the queue constructor from the old implementation, and the new one will now be called queue. Now, the reason we're doing that is because we're going to use the simple original implementation to help us test the implementation that we're constructing here. Okay, so let's have a look at the implementation. Okay, let's look at the implementation then. So as you may have noticed, we're going to represent the new kind of queue. That is to say, implement the queue using two lists, one list to represent the front of the queue and another list to represent the back. And so, for example, the empty queue will be represented by an empty front and an empty back. When we add an element to a queue, we're going to add an element, well, let's call it A, onto the front of a queue, which has a front and a back. And what we get by doing that will be a queue where we take A and put it on the front of the front, and the back of the queue is unchanged. Is that right? No. It was just in the same way as before. The A doesn't go to the front of the queue. If you just join a queue, you don't go to the front, you go to the back. Now, in the old version, we had to use the append operation to put the A to the back of the queue. But this time, the back of the queue is represented in reverse order. So the newest guy will be put on the front of the second list. And we go back to our slide, that picture that represents that. When a new guy comes in, we put the new guy on the front because these guys are represented in reverse order. So the back half of the list, the back chunk of the list, will be represented in reverse order. And that's what makes this queue a fast queue, because it's quick to add somebody and quick to remove somebody. Okay, what about removing somebody from a list? Well, this one requires a little bit more pattern matching. We can remove somebody from a non-empty list. So what does a non-empty queue look like? Well, we're going to remove whoever's at the front of this, and let me just put an underscore there to indicate that I really don't need that. And the result of that will be a queue with just a front and a back like this one here. So we've matched against a queue, and where the front of the queue has something on the front, we've thrown it away and given the slightly smaller queue. And the front uses a similar pattern match, not quite the same. In the front, we actually care about who's at the front of the queue, but what we don't care about is what the rest is, or what the rest of the queue is. So I'm going to use under don't care patterns here to indicate that. So let me line those up a little bit. And the final case is when a queue is empty. So when is a queue that looks like that? Is a general queue empty? Well, it's empty precisely when the front is empty and the back is empty. So that's our first attempt at representing queues using two lists rather than one. So this is how we're going to test this guy. So I've already got the code here ready. We're going to convert queues using this data type into the old version of queues that we had on the previous module, the slow queue that we're calling them here. And we're going to convert this kind to this kind in the following way. We take the front of the queue and the back of the queue and we join the two together. But we join them together into one list in such a way that now the back has to be reversed. because this is represented in reverse order. So we get a slow queue representation from the fast queue by joining the front to the reverse of the back. So we have a conversion function. And the conversion function allows us to state a bunch of properties, a bunch of invariant properties that relate this implementation to this simple implementation. Okay, so if we're going to do some testing, we need to have the ability to generate arbitrary queues so that quick check can actually test these things. So we need to do a new instance of arbitrary, which is queue of A. So we can generate arbitrary queues, some type A. And the definition is that we need to define the arbitrary function, or the arbitrary generator. So how are we going to do that? Well, a queue of A's is built from two lists of A's. So we can generate two lists of A's. Then we can put them together to form an arbitrary queue. So let's do that. Let's do the following. Let's take the front to be an arbitrary list and the back to be another arbitrary list, and then we return the queue that we formed from the front and the back. So there's a first attempt. Let's try and compile that. That didn't go so well. So what does the error message say? No instance for arbitrary A arising from A use of arbitrary. Possible fix, add arbitrary A to the context of the instance declaration, blah, blah, blah. So what we're trying to do here is generate the arbitrary front of the list and arbitrary back of the list. This is a list of A's and this is a list of A's. But you can't generate an arbitrary list of any type A. It has to be a type A which you know how to generate. Right? So we're trying to generate a list of A's here and a list of A's here. We can only do that if A itself is in the arbitrary class. So actually you can have an instance declaration that has a type constraint, a class constraint, and that is that if A is in the arbitrary class, then we get an arbitrary at this type. So we need a constraint, which is this thing here, and this says if A is in the arbitrary class, then we are putting QA in the arbitrary class as well by defining this function. So let's try that. That should hopefully, so we can sample arbitrary at type Q of, let's say, int. So it's not a queue of int, it's a generator for queues of ints. We're sampling that one there, and there we see a bunch of samples because they're printed out because we've derived show for this thing. Okay, so having done that, we can do some testing. And in the process of testing, we will see that we haven't quite finished our definition. So let's try some quick checking of, let's say, remove. Okay, that failed pretty quickly. We try to test removing in the case when both lists were empty, and then that will fail. So we have some operations that will fail, and that's what they're intended to do. So what we've done wrong is not implement them incorrectly, but we've actually specified the property incorrectly. This only holds if Q is not empty. So we can represent that using the quick check operator to filter. So we can say not is empty Q for all queues which are not empty. This property holds. So this is an invariant that should always hold for the arguments to this function, and we can represent those. So now they're kind of documented, and that's not only true of remove, but also of the add. So let's have a look at what happens now when we try that one again. Oh, we still have a problem. We have a non-empty queue. There it is, which still causes us to fail. So what's going on here? Well, what we've got is we've got the front of the queue is empty, but the back is not empty. Now, that's not a good case. We don't really want to end up with the front becoming empty when the back is not empty. What we need to do is move the guys at the back of the queue to the front of the queue to make sure that that never happens. So in fact, that's a general invariant of the data type. That is a property that should always hold of the data type. Namely, that if we have a queue, then the front of the queue should never be empty if the back of the queue is empty. So how are we going to express that? Well, one way to do it is to say that it's never the case that the following holds: that the front is null and the back is not null. So that should never hold. So it should never be the case that the front of the list is empty and the back is not empty. So that's a property that we expect to hold, we want to hold for all queues. But we're not going to get it for free. We're going to have to make sure that that always holds. But if we're going to test it, we better make sure that we never generate queues that have this property. So what we need to do is to make sure that we build queues so that if the front is null, then the back is also null. So we can do that here. We can sort of generate random arbitrary front and back. But what we can do is say if the front is null, then we'll build the queue back front. Otherwise, we can build the free queue front back. So we've got a candidate front and a candidate back, but we might actually swap them round if this one turns out to be empty. Okay, so let's reload that. Let's test the invariant. So the prop invariant now will test our generator. It tests that we never generate anything which is bad, and that is indeed the case. So the generator is good. We never inviolate the generator. So now let's go back and test some of the earlier cases. Let's try the property remove, and we see that works very well. Everything seems to be okay because we've generated. Let's try some of the others. Let's try. Quick check, prop, add. That's also great. But what are we actually checking with that? Well, we're checking that the implementation we have here agrees with the original implementation. But what we haven't checked, what prop add does is it creates a new queue. So any operation which creates a new queue, we need to make sure that it satisfies the general invariant property that we expect for queues. And that's this one here. So what we should also test, so a lot of tests going on here, is another invariant. So let's separate these testing of the comparison between the two structures and the invariant. But the property of the add, the invariant for add, let's call it prop add inv. If we have an element A and a Q, then adding A to Q should satisfy the invariant. So when we add A to the Q, then the result should satisfy the invariant that we have above. And then the same goes for testing not only add, but all the other operators. For example, the empty case. The property invariant for empty. And also the remove function. The property remove function should be such that if we remove something from the queue, then the result should satisfy the invariant. But of course you have to remember that this guy will only work if the queue is non-empty. So we better add that constraint, that filter to our quick check property. So only works if the queue is non-empty, of course. We don't expect it to do anything sensible for an empty queue. Let's put those all, format those all. So there are our three invariants. Let's try one of them out. Let's reload that. Oops, I've got a multiple declaration. Oh, it's the invariant that I'm defining. Okay, so let's quick check one of those. Let's have a look. What did we do before? Prop add. Let's add the invariant. Whenever we add something, do we satisfy the invariant? And we don't. When we add something to the invariant, you see actually we're testing at the very simple type of blobs, but actually it doesn't matter because it still catches the error. What happens when we add something to the empty queue? Well, we add this to the back of the queue. But as soon as we do that, we fail to satisfy the invariant. The invariant fails. Let's try the other one as well. Let's try remove. We also have that. If we remove something from this queue, what we do is we take out this element from the front, and we end up with a queue which does not satisfy the invariant. So we need to fix our definitions to make sure that the invariant is always satisfied. So where does the invariant go wrong? It can go wrong in both remove and add. And it goes wrong precisely when the front ends up being empty. So we're going to fix this in a simple way by saying, well, what we've done here is we've used this kind of rather stupid constructor, the constructor that just blindly puts these two things together. And the constructor shouldn't just blindly put them together, it should make sure that the invariant is satisfied. So the way it can satisfy the invariant is to make sure that whenever the front is empty, we move the back of the queue to the front. So what we're going to use is a smart constructor called fixQ, a little function. And let's define it down here. So fixing a queue, if we have an empty front of the queue and the back of the queue, we need to fix it. Fixing a queue with a front and a back where the front is not empty, we don't have to do anything. We simply build the queue from the front and the back. But in the case that the front is empty, we'll take the whole of the back of the queue and we'll shuffle them over into the front of the queue. That is to say, we're going to build the queue by reversing the back of the queue and putting them in the front. And now we have an empty back of the queue. So the waiting room at the front is now empty. So we shuffle everybody who was at the back of the queue into the front, leaving the new back empty. So this will guarantee that we will satisfy the invariant. So if we reload now and we try those, then we'll see what we should pass those. And indeed we do. So we did so by replacing the stupid constructor by a smart constructor, one that applies a little bit of intelligence before building the resulting queue. Now, one thing you might notice here is that the whole point of this representation was to be quicker than the other, more efficient than the other version. And now we're using a recursive function. But we only use this recursive function when the front becomes empty, and any element in the back only gets shuffled to the front once in its lifetime. And so every element is responsible, the reverse is responsible for one extra computation step for every element that ends up being removed from the list. And that's a small constant overhead for each element, so it's not a big cost that we had potentially in the slow version. So this cost here averages out, it amortizes over the cost of manipulating all of the elements of the list. So the final thing we need to do to wrap this up is to package the module in such a way that these are the only operations that are exported. So the idea will be to explicitly list all the things which this module will export. So we can restrict so that all the testing functions will be internal. We use them to test this module when we're inside the module, but the thing that's visible to somebody who imports this module will only be the type of queue and the operations of the queue. So the way we do that is to specify a list of the things which we will export from this module. And I'm going to export all of these guys, but let me just put them in a comment sequence here, together with the data type for the queue. Now we can't actually leave the types in here, although it's nice to see the types in the head. I think so I have to comment them out. So there's the list of the things that this module is exporting. So we can compile that. Now, what is this actually exporting? Which queue are we talking about here? Is it the data type or is it the constructor? In fact, this is the data type. We're exporting the type, but not the constructors. If we want to export a type and the constructors, then we would write something like this, all of the constructors. Or if we wanted to export a named constructor, well, we only have one. It's called queue. So why do we not export the constructor? Well, if you export the constructor, that means that the constructor can be used to build queues which do not satisfy the data type invariant. And we don't want that. We've made sure that whenever you build queues using these operations, you always get a queue which satisfies the data type invariant. And that was needed to actually make this work properly. And we tested for that. But if we allow somebody who imports this module to build their own queues using the constructor, then they could build something nasty. So let's look at an example of that. Here's a Haskell file that's empty, except that I've imported that file. So let me just compile that. So now I can use, for example, the empty queue to build an empty queue, and they're still printed out, so we probably want to change the show function for that to hide the representation. But that's not the point I wanted to make. The point I wanted to make is we don't have access to the queue constructor. So we cannot do bad things like build, that would certainly be bad, to build a queue which had an empty front and a non-empty back. And the reason we can't do that is because the constructor for building queues is not in scope. It's not one of the things which was exported by the queue module. So we have no choice but to think of queues without thinking of the way that they're represented. Of course, that requires us to change the show function, but that's very straightforward to do. We won't bother to do that here. And so, very specifically, an abstract data type in Haskell is always represented by a module and a type constructor, a type where the constructors are not exported. Now we may want to do this in two steps, to have a module which exports the constructors, a kind of internal version that we might want to do testing on. But the main thing is that the main representation of the data type is a module which exports a type and a bunch of operations on that type, but nothing else.